This afternoon, we are going to discuss about model and simulation. And we are going to have two sessions. In the first session, we are going to have a presentation from our speaker. And the next session, we are going to ask and answer session. And then lastly, we are going to have a photo session at the end of this session. So during the presentation session, everyone kindly turn off the microphone and turn on your camera so you're able to see your face. And then on the question session, kindly raise your hand if you have a question, or you can type on the chat box. So on the first session, I would like to invite Dr. Helmi to be the first presenter. So Dr. Helmi, the stage is yours, please.
Thank you so much, moderator. So I will try to share my slide first before we start. Okay, can you see my slide?
Not yet. This is your first page of your slide, yeah?
Yes.
Okay.
This one, is it? You can see?
Yeah. Yes, we can see it.
Okay. Okay, baik. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good evening, everyone. Alhamdulillahirabbil alamin wassalatu wassalamu ala asyrafil anbiya wal mursalin sayyidina Muhammad wa ala alihi washabihi ajmain. Thank you so much, moderator, and also Dr. Don Pradana from TelU University. Ladies and gentlemen and distinguished participants, good evening and welcome to the online joint class. This is a collaborative program between Telkom University Indonesia and also University Kuala Lumpur, Malaysia. So, I'm honored to be here today as your invited speaker. I'm Dr. Helmi Adli, a senior lecturer from Technical Foundation section. Actually, Technical Foundation section is we have two types of lecturer to fill. Okay, one is IT, information technology lecturer, and also mathematics lecturer. So we are from University Kuala Lumpur, campus of Malaysian Institute of Industrial Technology, whereby it is a city of Johor Bahru, Johor, because UniKL in Malaysia we have 12 campuses. So this is campuses from Johor Bahru, Johor. First and foremost, I would like to extend my heartfelt gratitude to both Telkom University and UniKL for organizing this remarkable event, which bring together the finest mind from across borders to share knowledge and insight. This collaboration serves as a testament to the power of global connectivity and importance of knowledge exchange in the world today. Today, I have the privilege of delving into a fascinating subject that holds the potential to unlock new horizons in our understanding and simulation, a gateway to understanding complex systems. Okay. In an increasingly interconnected and complex world, the ability to model and simulate complex systems is more critical than ever before. Throughout the course of this session, I cover into the topics of modeling and simulation, exploring how it acts as a gateway to comprehending complex systems that range from natural phenomena to technological innovation. We will explore how this powerful tool aids us in predicting outcome, optimizing process, making informed decision across a wide array of domain. Without further ado, let us begin our exploration of modeling and simulation, a gateway to understanding complex systems. Our journey today will be divided into 5 sections. Number 1 is introduction to modeling and simulation. Topic number 2 is historical context and evolution. Topics number 3 is in various fields. Number 4 topic is current trends and future directions. And I'll conclude in the topics 5. Introduction to modeling and simulations. Let's start at the beginning. What exactly are modeling and simulation? Okay, in the simplest terms, modeling is about creating a simplified representation of a complex reality. Think of it as a drawing map. Okay, as a drawing map instead of showcasing the entire territory. This model could be anything from a diagram to a mathematical formula representing a system or a process. Okay. On the other hand, simulation is where the magic happens. It's like bringing the map to life. Okay. By running experiments on our model, we can observe how systems behave under different conditions without the risk or cost associated with the real world testing. Together, they form a powerful tool for understanding and exploring complex ideas. So as you can see from the figure, it shows that a flight simulator used by a pilot, okay, maybe trainee pilot, okay, before they really fly the real airplane. So now I will share with you a video explaining what is simulation all about. Okay, give me maybe 30 minutes. I will show you another video about this.
What is simulation, and how can you use it to improve processes? Simulation is a uniquely powerful approach for making confident, evidence-based decisions that will improve your organization's efficiency and profitability. So, how does it work? Simulation is an effective technique for imitating an existing or proposed process. Software like Simulate enables you to build a visual representation of your process, similar to making a flowchart. Add rules for activities and resources, and the simulation will mimic real-life behavior. It's animated, so you can quickly see bottlenecks, overutilized resources, or any under-resourced elements. Make changes and see exactly how they'll affect the process in real life, without any risk, impact to your current performance. What can you simulate? You'll gain most benefit from simulating any process that's complex or costly to experiment with in real life. These might involve uncertainty, complex interactions, or elements of randomness, like varying customer or product arrival patterns. For example, reducing lines at a store checkout. You can simulate the possible behaviors. If the customer is served straight away, joins a line, or uses a self-checkout. By simulating arrival patterns over the week, you'll quickly see what will happen at peak times and where checkout lines are building up. Using this simulation, you can then quickly test ideas to reduce lines. You could add more employees, change work schedules, or add more checkout systems. You'll see exactly how each change will impact performance. Compare the results and costs to find the solution that reduces queues and delivers the best customer experience. When could simulation help you? If you face complex decisions, assess how changes will impact every aspect of your process in a risk-free environment. You're having problems with the process. Quickly highlight any inefficiencies in a process that could be impacting your bottom line. Your process doesn't exist yet. Plan new process and validate your ideas ahead of any investment. You need to understand the long-term impact of decisions. Test different scenarios and simulate weeks, months, or even years into the future within seconds. You need to build stakeholder buy-in. Easily communicate concepts through a visual and animated approach to process improvement. What challenges could you solve with simulation?
Okay, I will continue with my slide. I will share it again. Now we move to second topics, historical context and evolution. The concept of modeling and simulation is not a product of the modern era. It dates back centuries, with early examples found in mathematical theories and mechanical simulators, like ancient planetarium, abacus as a mechanical calculators from ancient China, and much more. These were the first step towards abstract representation of reality. However, a significant leap occurred during World War II. Nations began to employ simulation for military strategy and training. Okay, crafting scenarios to prepare for a strategize against real-world event. This era set the foundation for what was to come: the integration of strategy, training, and theoretical concept in simulation. And here you can see from the figure, this is the sample of the 17th century of mechanical calculators in 1642. Okay, nowadays we have our own calculator in our handphone, in smartphone, right? So 17th century is this like this one, this very big calculator. Okay, so this is the 17th century, the previous era. The mid-20th century marked the dawn of new era, the computer age. This period revolutionized modeling and simulation with the emergence of digital computers in 1950s and 60s. Simulation took on the new form. For example, Monte Carlo methods allow for complex probabilistic simulations. As we move into the 70s and 80s, advancement in computer graphics and processing power opened new avenues. Simulation became more visually detailed and computationally intensive, providing deeper insight and more realistic of the real world. Okay, this era was a game changer, setting the stage for the sophisticated simulation as we see today. Entering the late 20th century, and moving into our current era, the landscape of modeling and simulation has been marked by rapid innovation. High fidelity 3D simulation, real-time processing, and the integration of artificial intelligence (AR) have become the norm. The 21st century further expand the scope with cloud computing, the Internet of Things (IoT), and also a virtual reality (VR). Today, simulation are not just about replication. They are about creating new realities, solving complex problems, and pushing the boundaries of what possible. The advancement in this era have transformed simulations into a crucial tool across numerous fields from medicine to environment science. We are diving into the dynamic and diverse world of modeling and simulation. It's more than just a set of tools or techniques. It's a game changer across numerous fields, changing the way we tackle challenges and craft new solutions. Consider how this technology touches so many aspects of our lives. In healthcare, for example, it's revolutionizing training, allowing medical professionals to practice without risk. In engineering field, it's behind the design of everything from robust building to intricate devices, ensuring their safety and functionality. Environmental experts use it to visualize climate change scenarios, guiding us in environmental stewardship. And that's just scratching the surface. Each use of modeling and simulation showcase its strength and potential, highlighting how it's driving progress in our society. I invite you to think about the vast possibility this field open up. So let's start this exciting exploration together and see where modeling simulation are making a real difference. Now, I will share with you a few videos application in various fields. Okay, give me a second.
Press the Start button to begin.
At these x-rays. As you can see, this is a significant fraction missing. See the patient's deep tissue. You will need to further dissect the deep tissue by using a scalpel incision to make a deeper incision, exposing the fibula.
Because again, this is an application.
Look at the side of the patient's neck to verify.
Excellent. You can now see the bone and fracture clearly. Place the forceps back on the tray. Use the screwdriver to drive in that first screw. Pull the trigger when you have the screwdriver screwdriver in position. Okay, place the screwdriver on the instrument tray. That was a very successful operation. Nicely done.
Okay, as you can see, this is a simulation in medical, whereby from this simulation is help a doctor to do some operation by using a virtual reality. Okay, next we move to okay, the importance of simulation in F1. F1 is stand for Formula One. Okay, Formula One. This is the car. So I will show you the video. Okay.
Formula One cars don't spend that long on the track, so we have to rely a huge amount on all our simulation tools to furnish us with the data and the analysis that we need to develop these cars.
We unfortunately are limited in the amount of testing that we're able to do on track. So the question is really, how do we make sure that what we do take is going to be as good as it can possibly be?
Over the last 10, 20 years, simulation tools have really come to the forefront, and also the margins that we're looking for are smaller and smaller and smaller. So having high fidelity tools, those results from those simulations are allowing us to make better and better, more informed decisions.
Simulation in all fields that we have has allowed us to make quite big steps in car modeling, in representing reality.
Doing it quickly, doing it efficiently, in a controlled environment. If you go to the track, it's often the air temperature or track temperature changes can actually dominate some of the results you're trying to achieve. Well, actually in the controlled environment of simulation tools, as long as your tools are correlated and giving good answers, then the power is limitless.
Once we have that simulation up and running, we can then do multiple setup changes. We can try new aerodynamic components all in the virtual world and understand how these are going to then work on track.
The Loop Simulator helps the drivers to learn the tracks in the first place, but then also work with the setup, work with different tires, work with different wing configurations. So also it's for the drivers a very, very good training ground to arrive at the racetrack very well prepared and ready to attack from the first lap.
The data science approach in recent years has allowed us to use the data from the car to help validate our simulation models. So it's like a closed loop system which is trying to always improve how good your simulations are.
And of course, simulation is only as good as the correlation to reality. So we spend a huge amount of time feeding back the information that we get from the car into all our suite of development tools.
And we've just seen in recent years, the bits that are really hard to simulate are the aerodynamics and the tyres, and that's where a lot of the focus is going into within our simulation tools.
And these simulation tools don't just extend to the track or aerodynamics. We have them in every aspect of any part of the car that we design or that we model. And the simulation tools that we are using improve year on year, and it's absolutely phenomenal what they can achieve now compared to what we were able to do 10 years ago.
We're forever trying to give ourselves better understanding of the marginal gains of how we can improve, and it's that how we can do better that we're always asking ourselves.
We're leaning more and more on artificial intelligence and machine learning in improving the correlation on our simulations as we replicate the car more and more accurately to allow the car to develop to an even higher level.
I think the future for simulation is really going to be dictated by where computers go and where things like machine learning go. We all know that there's great potential for the future, but understanding exactly what things like machine learning, deep learning can actually offer us in the simulation environment is really going to be key to how these tools develop in the future.
Okay, that is the importance of simulation in F1, okay, F1, Formula One racing car. So I want to move to second video. It is a flight simulator. The second video is for Airbus 320 full flight simulator. I need to make it again. The share screen. Okay.
With our own technological solutions and complete design and development, we at Indra offer state-of-the-art technology in our simulators and training solutions. Leaders in simulation in Europe, we have platforms already available for Airbus 320, Boeing 737, Airbus 330, and ATR 72500. We maintain a continuous effort developing new platforms and improving our technologies and training solutions. Our Level D full flight simulator has the highest realism at its aim, with full cockpit with real and replicated aircraft parts, using the manufacturer hardware for the sensitive parts. Simulating all environmental and weather conditions with perfect visual correlation. Great training value with a complete malfunction set covering and surpassing the aircraft manufacturer recommended set and including customized malfunctions for the customer. We integrate our own state-of-the-art visual solution with a highly customizable airports database, including Level D specific airports, basic airports, and real-time airports. Fully electrical motion system and digital control loading system, fulfilling the highest standards of the industry. We pay attention to the little details, providing a comfortable and ergonomic forward-facing instructor station with a great crew visibility. Apart from Level D full flight simulators, we at Indra cover all the range of training solutions. As with our ICAT, our flat panel trainer, the most cost-effective high-fidelity training solution, certifiable level 4 EASA and FAA. We at Indra are deeply aware that a simulator is a critical tool for our customers, and it has to stay in perfect condition for many years. Because of that, we put special effort in designing and manufacturing our simulators to be easy to maintain, using only the best quality and reliable components and taking maintainability in all design and manufacturing phases in great account. We offer a wide range of post-delivery support options through our World Global Support Network. Decades of experience and references back us up. Indra, we are our customers.
Okay, After Airbus, I want to show you another one is weather. This is for weather simulation.
The weather. It's unpredictable. Forecasters, using some of the most powerful and expensive supercomputers in the world, have a tough time just trying to tell us if it's going to rain next week. They're pretty good, but they don't always get it right. University researchers are developing a new way to improve the computer models that are so vital to good forecasting. But they're not using expensive supercomputers, just the humble laptop.
The model's called the Weather Research and Forecast Model, and it's a high resolution, so it can simulate small-scale weather like thunderstorms and clouds.
Only recently have laptops been powerful enough to run this kind of model.
Nowadays, they are resolved on supercomputers in much greater detail than can be done on a laptop. But the opportunity here is that now you can actually run on a laptop a pretty decent simulation that captures the key features of the thunderstorm.
Dr. Chris Chambers tested his laptop out on a thunderstorm called Hector the Convector.
Hector is a thunderstorm that forms over the TelU Islands near Darwin, and it is a very reliable weather event. Almost on a daily basis, this thunderstorm will develop as the island heats up, so it becomes a very useful weather phenomenon to study in science.
One of the huge impediments to forecasting thunderstorms is the difficulty of initializing or starting the computer models with the correct data. The main data that people are using to start these models off is radar data, which is great. There's lots of things that you can do with radar data, but it's expensive to collect. Instead of just using radar data, why not use visual observations, which are very cheap and easy to collect?
Dr. Chambers tested the accuracy of his model against a time-lapse video produced by the Brisbane Storm Chasers.
This video shows a comparison with the model simulation on the left and the time-lapse on the right, and it's looking towards the Tiwi Islands off Darwin. As we set the simulation running and the time-lapse running, the clouds can be seen to be moving in the easterly winds in the lower atmosphere. And then as the island heats up, the thunderstorm develops in the time-lapse, and then slightly delayed in the model, the same thing happens. If you pause at this point, you can see that the tops of the thunderstorms exhibit a similar structure, both in the time-lapse and in the model. So the model is capturing the main structures of the thunderstorm during this particular period.
One of the issues with using visual observations for this type of sophisticated model is that it's pretty early days at this stage. There's a lot of technical issues to overcome before the potential of that type of observation could be fully realised in a thunderstorm forecast of this kind.
If you have these time lapses and model comparisons going on, you can compare them as they are unfolding to see whether the model is actually correctly simulating what's going on in the atmosphere. And this could be done on a very large scale. You could have webcams in many places, model simulations running on computers, laptops, anywhere.
One of the changes that has occurred in the past few years is that now many different people are able to run these type of simulations. People who don't have access to a supercomputer, people who can start to experiment with these type of models on their own and hopefully start to come up with a wider range of scientific conclusions on these type of simulations.
Okay, next I want to move another video whereby this is for your information. I'm here in UniKL. I'm teaching modeling and simulation for student bachelor in industrial logistics and also master and supply chain management. Okay, and how modeling and simulation helps industrial logistics as master supply chain management. It is include processing such like supply chain, warehouse manufacturing, transport planning, and so on. So here I would like to share a sample of video of supply chain simulation. Okay. Okay, this one.
Manufacturer was constructing one of the A chemical manufacturer was constructing one of the largest petrochemical facilities of its kind, designed and built in a single phase. The production facility had limited space for on-site storage and produced goods that would be shipped via 2 ports to destinations worldwide. The sheer size of the system and high amounts of variation made it difficult to understand system bottlenecks with traditional static spreadsheet calculations. The client contacted Mosimtech to develop an end-to-end dynamic simulation model using Simio simulation software to understand the holistic system both visually and analytically. Some of the components in the model included discrete and continuous production, production scheduling, on-site warehousing, empty container management, raw material replenishment, and truck and rail transport. The model extends past the fence of the production facility to include bulk and container port logic, ocean carriers, hub delivery, and regional consumption. The holistic supply chain model utilizes a combination of push production and reordering logic to trigger activities within the detailed production facility model. All user inputs can be modified through a custom Excel-based interface, providing a structured means of model analysis along with input data validation. Input controls are extensive, including product-specific packaging types, production cycles, customer demand, individual resource schedules, capacity ramp-up curves, weather impacts, and more. The user has the ability to introduce and represent randomness throughout the model inputs. The model can be used for communication and visualization by executing at runtime speed, allowing the user to navigate through the 3D representation as needed, following predefined views of the key system areas, or following specific material handling equipment and containers as they flow through the system. Extensive statistics are being recorded and support scenario analysis with detailed model outputs available for view in raw format, pivot tables, and state-of-the-art custom dashboards. Stakeholders were able to visualize the entire planned system and utilize model output to understand capacity constraints before committing to final designs. The model continues to be available for operational decision-making as the task of actual facility construction progress and site operation gets refined, including decision support regarding supplier contract.
I think Dr. Helmi is out from this Zoom meeting. Could everyone kindly please wait? Maybe he has a technical issue. So please everyone. So please wait, okay?
Okay, so I got my back. I'm facing internet connectivity problem here because here we have here rain heavily, rain heavily. Okay, rain heavily here with thunderstorm. So I will continue my slide. Mr. Dr. Don, is it okay?
Hello, Dr. Helmi. Yes, you still have time to continue your presentation.
Okay. How about the weather there, moderator? Here we have very rain heavily here with thunderstorm.
Yes. And here, Dr. Helmi, we also have heavy rain right now, currently in Bandung.
Okay. Okay, so we are same weather right now. Okay, I will continue.
Yes.
So next is what is the current what is the current trends and future direction for modeling and simulations? Okay. So let's talk about where we are headed with simulation technology. Okay, first up, the digital revolution. For example, artificial intelligence and machine learning. These are not just a buzzword, but they are reshaping simulation as we know. Imagine simulation that not only model complex system, but also learn and adapt as they go. So this is another enhancement of the modern simulation. We are seeing this in everything from autonomous vehicles testing to financial forecasting. It's like it's constantly evolving and getting smarter. The possibilities, yes, the possibilities maybe they are as limitless as our imagination right now. Imagine for a moment simulations that learn, that grow smarter with each iteration. This is no longer the stuff of science fiction, it's the reality we are crafting as we speak. Artificial intelligence and machine learning are the new alchemists, turning data into gold, providing insights that were once hidden in the noise. Think about the last time you heard the term predictive analytics. In sectors like finance, we have got simulations that are forecasting market trends with an uncanny precise. So thanks to this technology that helps us to do a prediction about the market trends. And in medicine, in healthcare, they are revolutionizing how we understand the human body, making personalized as we stand on the base of what some call the fourth industrial revolution. It's clear that AI, machine learning are not just tools, they are partners in our quest to build a smarter, more connected world. And the digital transformation here will guide us to. And then the second current trend is virtual reality and augmented reality. In gone are the days when simulation were confined to computer screens. Today, we are stepping inside our simulations thanks to virtual reality and augmented reality right now. from training surgeons, as you can see from my video, from the training surgeons with life-like experience without stepping into, and or architects walking through building before they are even built. Virtual reality and augmented reality are not just changing the game, they are creating a whole new playing field. It's about making simulations more intuitive, more immersive, and I would like to say it will be a bit more fun, okay, in the future. As a wrap up on our journey through the dynamic world of modeling and simulation, let's take a moment to reflect what we have discovered. We have seen how these powerful tools are not just about predicting outcomes or solving complex problems. They are about shaping the future and our future. From healthcare to environmental science, from engineering to social science, modeling simulation are at the forefront, driving innovation and progress. What truly exciting is that we are just scratching the surface. As technology evolves, so will the capabilities and application of this simulation. And you, as the next generation of thinkers, as a students, innovators, and problem solvers, have a unique opportunity to be part of this exciting evolution in modeling and simulation in the future. Whether it's in a research application or development, your contribution can propel these technologies to new heights, create a better, more efficient, and also more understanding to the world. So I would like to encourage all of you to stay curious, keep exploring, and remember that in the realm of modeling and simulation, the only limit is our imaginations. So thanks thanks to all the participant, to Dr. Don, moderator. Thank you for your attention, and let's to continue to push the boundaries of what's possible together. That's all for me. Thank you so much.
Thank you, Dr. Helmi, for the presentation. So moving on to the next session, I would like to welcome Dr. Doan to present your presentation. So, Dr. Doan, the time is yours.
Okay, thank you, Mr. Sena. Okay, I would like to share my slide. It's already seen.
Yes. Yes.
Okay. Okay. I will be start. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Thank you for International Office. This program, online joint class, is a collaborative program between Telkom University Indonesia, Bandung, and University Kuala Lumpur, Malaysia. The topic after this afternoon is about the model and simulation. For this session, I will be present about the topic model and simulation, especially for 5G and Internet of Things system model. This is the part of my lecture in Telkom University. My name is Duan Pertana. I'm a lecturer in Telkom University, subject telecommunication engineering. Yeah. Now I will be continue about the session about the model and simulation. Firstly, about the outlines, I will be introduced about what is the system model and what is the simulation and step in the simulation and model building. And the second part is about the 5G system model. Firstly, start about what is 5G or 5G system model, and then 5G NSR, non-standalone, or SR, standalone mode architecture, and then 5G architecture diagram and the difference between 4G, 5G network architecture. And the third, I will talk about the Internet of Things system model. Firstly, about the Internet of Things. What is the Internet of Things? Based on the ITUT, yeah, technical overview, and of course, I will discuss about the Internet of Things of architecture. Okay, now we're going to the first session about the what is the system model. Like Dr. Helmi talk about the system model. I think it's already present with Dr. Helmi. System model is a representation of an object, a system, or idea in some from other than that of the entity itself. I think it is the basic fundamental about talking about the system model based on the Shannon theorem. Now we go to the what is the simulation. When we talk about the simulation of system, is about talking about the operation of the model, which is a representation of the system. The operation of the model can be studied from the properties concerning the behavior of the actual system that can be inferred. Now we go to the step in the simulation and model building. Firstly, is we define about the achievement purpose. What is the system purpose or the goal? And then the second, we choose the appropriate simulation tools. And the third, we start modeling the appropriate level of detail. And the fourth, we start early to collect the necessary input data. And the next step in the simulation and model building is provide ongoing documentation. And next, we're going to verify and validate the model system. It seems it is okay from the model or from the simulation side. And the end of the step is develop a plan for statistical output analysis. Now we're going to talking about the 5G network model. We start from the explanation from this video.
Hey guys, in today's video I'll take you through the 5G network architecture in a simple way. Now I know network architecture can be complex when you focus on all the nodes, interfaces and various technology scenarios like interworking with earlier generations of mobile networks. But what I'm going to do is that I'll first show you a highly simplified view of the 5G mobile network, and I will then show you a slightly more detailed architecture to explain most of the network nodes used in 5G networks and their responsibilities. The radio network in 5G consists mainly of the cell tower next generation node B, known as the GNB. A GNB may be split into two entities, GNB Central Unit, CU, and GNB Distribution Unit, DU. It is possible to implement both the central and distribution units in the same GNB, but having the distribution unit DU closer to the user location is also possible. The distribution unit DU is responsible for real-time scheduling functions, that is, which device should communicate when and what radio resources like frequency, time slot, etc. to assign to which device. Central unit deals with non-real-time functions. Central unit works with the higher layers of the network protocol stack, whereas the DU, or distribution unit, works with lower layers of network protocol stack, for example, physical layer, MAC, and RLC. The DU is closer to the site, whereas the CU, as the name suggests, can be at a central location. The split allows bringing the DU closer to the location of phone users, and this split can be crucial in use cases like edge computing by bringing data closer to the user's location. The 5G core network consists of several nodes, which we will look at in the next slide. Generally, the key nodes representing the 5G core network in most documentation are AMF and UPF. UPF is a user plane function, and AMF is the access and mobility management function. Let's now look at the nodes and functions that 5G networks use. The network architecture can be seen at least two levels, the user and control planes. The control plane carries control functions such as signaling traffic, and the user plane carries user data, for example, the content of the YouTube video you may be watching on your phone. A mobile phone is connected to the base station GNB, linked to AMF and UPF in the core network. UPF user plane function, which as the name suggests is part of the user plane and connects a mobile phone via G-Node B to outside networks like the internet. UPF is connected to the session management function, SMF, in the control plane. UPF oversees service quality and applies policies that the PCF, policy control function, sends via SMF. There can be more than one UPF, and for low latency communication, local UPF can be used to avoid transmission delays due to long distances. Let's now talk about SMF, or session management function. SMF establishes and manages the sessions between a user device and the mobile network. It takes care of the management of IP addresses for the devices. It is also responsible for selecting UPF for the user device and controlling the UPF. Finally, SMF is also an interface between the UPF and the policy control function PCF, where policies and business rules reside. AMF, or Access and Mobility Management function, is part of the control plane. It is connected to the G-Node B and provides access and authentication. Network Slice Selection function, NSSF, determines which AMF or AMFs can serve a particular UE based on the service type the UE is trying to access. UDR, or Unified Data Repository, is a database where all the subscription, application, and other data reside. With Unified Data Management, UDM, credentials. And finally, NEF, or Network Exposure function, exposes the 5G core network capabilities to third-party apps, developers, and companies. It opens up network services, for example, voice calls, data connection, etc., to third-party applications in a highly secure and robust way through APIs and SDK. That way, third-party companies can create tailored services by utilizing cellular services, allowing a mobile operator to extend their And finally, NEF, or Network Exposure Function, exposes the 5G core network capabilities to third-party apps, developers, and companies. It opens up network services, for example, voice calls, data connection, etc., to third-party applications in a highly secure and robust way through APIs and SDK. That way, third-party companies can create tailored services by utilizing cellular services, allowing a mobile operator to extend their network footprint. Thanks for watching the video, guys. I've written a detailed post on this topic, and the link is in the description.
Okay, yeah, we continue about the 5G system model. Yeah. This is the main requirements for the 5G use case. Very type of the use case in the 5G autonomous vehicle control. About the latency, 5 millisecond, availability 99.99%, and reliability also same. And Indonesia is now we have some high speed train for in the 5G. The use case high speed train is about the traffic density tunneling is 100 gigabit per second per kilometer per segi. And then user throughput is for the downlink is 50 megabit per second, and the uplink is 25 megabit per second. Mobility is 500 kilometer per hours, and the latency is 10 millisecond. The main requirements for 5G is about the massive the network should be delivered the data much lower cost per bit compared with the network of today. The increase in data consumption will be result in increased energy footprint from the networks. I think from that 5G must be consumed significantly about the lower energy per deliver per bit. The other requirements for 5G is very low latency. It's for the end-to-end latency is about the 1 millisecond or less. And the other 5G requirements is very high data rates. The 5G should be support the data rates exceeding 10 gigabit per second in indoor and dense outdoor environments. The data rates of several achieve 100 megabit per second in urban and suburban environments. The other 5G requirements and capabilities is about the energy efficient networks. It's important for reduce the operational costs, and then the energy efficiency develop for the net off grid and the network. Energy efficiency is essential for the realize the operator ambition for the providing wireless access in a sustainable and more resource efficient way. This is the architecture 5G for non-standalone and standalone. Yeah, I think as already explained in the previous video, for the 5G non-standalone network using still using 4G radio element, and the core network is using for the 5G network architecture. It's more efficient using the architecture for a 5G standalone architecture. I think for the radio access network and the 5G network is fully using the 5G network architecture. This is the 4G architecture diagram for the UE, AU-TRAN, A-Node-P, and split for user plane and control plane. This is the 5G architecture diagram. As already explained for in the previous video. Firstly, the user equipment, and then next going to the radio access network, and this is for the core network. This is the difference between 4G 5G network architecture. The left picture is about the 4G architecture network architecture from the UE user equipment, and going to the radio access network and go to the core network. The core network is split within the 4G core network and for the application. It is the difference between 5G network architecture from edge cloud from the user equipment, and then radio access network, and going to the edge cloud. For edge cloud in the 5G network architecture, it's content for 5G core for user plane and for application. This is the feature we going to the 5G network. It's a 5G network slicing is enable service providers to build virtual end-to-end networks to application requirements. For the example, for the mobile broadband equipment is delivered for mobile broadband services, communication, entertainment, and internet. And the other is for the machine-to-machine equipment, or deliver about the massive IoT slicing for the application, retail, shipping, manufacturing. And the others is reliable low latency, RLC, deliver about the mission critical IoT slicing for the application automotive, medical, and infrastructure. This is the 5G evolution. For the data rate, we can 5G ready is 500 megabit per second, and for 5G sub 6 multi gigabit is up for 1 gigabit per second. This is about the 5G radio access, the capabilities and technology, the high frequency band access and vehicle integration, device to device communication, D2D communication, and flexible duplex, flexible spectrum usage, and multi antenna transmission, and also ultralink design. Okay, now we going to the second part about the Internet of Things system model. To start about the Internet of Things system model or IoT system model, we going to watch the video.
The Internet of Things, or IoT, is influencing our lifestyle from the way we react to the way we behave. From air conditioners that you can control with your smartphone, to smart cars providing the shortest route, or your smartwatch which is tracking your daily activities. IoT is a giant network of connected devices. These devices gather and share data about how they're used and the environment in which they are operated. It's all done using sensors. Sensors are embedded in every physical device. It can be your mobile phone, electrical appliances, vehicles, barcode sensors, traffic lights, and almost everything that you come across in day-to-day life. These sensors continuously emit data about the working state of the devices. But the important question is, how do they share this huge amount of data and how do we put this data to our benefit? IoT provides a common platform for all these devices to dump their data and a common language for all the devices to communicate with each other. Data is emitted from various sensors and sent to IoT platforms securely. IoT platform integrates the collected data from various sources. Further analytics is performed on the data and valuable information is extracted as per requirement. Finally, the result is shared with other devices for better user experience, automation, and improving efficiencies. Let us look at a scenario where IoT is doing wonders. In an AC manufacturing industry, both the manufacturing machine and the belt have sensors attached. They continuously send data regarding the machine health and the production specifics to the manufacturer to identify issues beforehand. A barcode is attached to each product before leaving the belt. It contains the product code, manufacturer details, special instructions, etc. The manufacturer uses this data to identify where the product was distributed and track the retailer's inventory. Hence, the manufacturer can make the product running out of stock available. Next, these products are packed and parceled to different retailers. Each retailer has a barcode reader to track the products coming from different manufacturers, manage inventory, check special instructions, and many more. The compressor of air conditioner has an embedded sensor that emits data regarding its health and temperature. This data is analyzed continuously, allowing the customer care to contact you for the repair work in time. This is just one of the million scenarios. We have smart appliances, smart cars, smart homes, smart cities, where IoT is redefining our lifestyle and transforming the way we interact with technologies. The future of IoT industry is huge. Business Insider Intelligence estimates that 24 billion IoT devices will be installed by 2020, and IDC predicts that IoT revenue will reach around 357 billion in 2019, resulting in a lot of job opportunities in the IT industry. Want to become a part of the IoT revolution? Come and master IoT with Edureka. The Internet.
Okay, we continue about the technical aspect on the model system for the IoT Internet of Things based on the ITUT standard. This is the recommendation or the standard for model system in IoT, Internet of Things. There are bunches of three model system. Firstly is the A model system. For the A model system is Internet of Things is defines for the connectivity of between device to device using through communication networks and also gateway. This is the first model system in IoT based on ITUT standard. And the second model is IoT is defined for the device to device communication using through communication networks without the gateway. The difference from the first model is the first model system is using gateway, and the second is without the gateway. I think for the telecommunication engineer is gateway is and the function is for the the connection from the internal network to external networks. And the third model system is IoT device to device directly without the communication networks and without the gateway. This is a three model system for the Internet of Things or IoT based on the ITUT standard. Moreover, furthermore, the based on ITUT, the devices in IoT is defines should be have 5 capabilities. Firstly, the device it should be able to sensing, and the second is actuation, and the third is data capture, and the fourth is data storage, and the 5 is data processing. This is about the IoT reference model. There are 4 layers from device layer, contains device capabilities and gateway capabilities, and the second layer is network layer, contains networking capabilities and transport capabilities, and the third is service support and application support layer, contains generic support capabilities and specific support capabilities, and the fourth is about the application layer, content of IoT application. Beside the 4 layer, we have some management capabilities in IoT and also the security capabilities. This is the IoT architecture. The bottom of the architecture is layer sensing, like a sensor gateway, sensor network, control gateway, home network, and etc. And the second session is network layer. This is the function for the network support using 3G network, LTE network, or Wi-Fi network, or using the integrated IP-based core network. And the top of the layer is application layer. This is like web or mobile application based on Android or iOS application. Yeah, this is the detail about the Internet of Things architecture. From the network of things, Wi-Fi, connecting device and router, and then ZigBee and wireless vehicle area networks. And the second is about the infrastructure. We have some cellular networks, cable networks, internet, or we have some satellite or cellular. And then the third is about the application interface, iOS, Android, or based on web. This is about the model system. Next, I am going to explain about the simulation. The simulation we have for the simulation in the telecommunication engineering, on the network engineering, we have some simulation. We use the network simulator 3, the simulator for the our base network system. What is the network simulator 3? Network simulator 3 is part of the network simulator or simulator based network. Writing in C++ programming and bindings in Python for the execution program. Network simulator 3 is using WAV build system. Network simulator 3 or NS3 is not an extension of network simulator 2 because network simulator 3 doesn't have any OTCL API. Network simulator 3 is new, have new visualization, yeah, in the networks. Network simulator 3 is a new simulator and discrete event networks. Network simulator 3 is a free and open source software that can be developed free in the internet. In the Wikipedia, we can get the source for the network simulator 3 software for free. And this is the simulation in the network simulator 3. It's, using a WES Wi-Fi based simulation, using wireless routing, MANET routing, mobile ad hoc network routing, LTE. We have LTE and 5G also in the network simulator 3. This is the network simulator 3 model system. Since the network simulator is based on a network system, is using the OC layer, layer 1 until 7 layer. This is the network simulator 3 feature, open source licensing and development. The second is based on Python script and C++ program. And then network simulator 3 is aligned with the real system and also can be integrated with the testbed. This is the how to the network simulator 3 works or the feature. Firstly, start from the topology definition, and then for the topology definition network. Sorry, network simulator 3 have helper API and containers, and then after define the topology, we define the model of the system like Wi-Fi or TCP/IP, and also, and then next we configure the for the attribute of the environment. Next, we execute the program, the simulation. The output of network simulator 3 is visualization and output analysis. This is the part of the network simulator 3 packet information. There are buffer, text, and also metadata. Okay, I think enough from me about the model and simulation in 5G and Internet of Things, and also the tool simulation using Network Simulator 3. Thank you. Enough for me. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Dr. Doan, for your presentation. Okay, everyone, moving on to the next session, we are going to have a discussion. So, everyone, if you have any question, kindly you can raise your hand, or you can turn on your microphone and ask the speaker directly, or you can put your question on your chat box. So, everyone, please. And I would like to remind everyone to, and at the end of the session, we are going to share the feedback link to get the certificate from this session. So kindly fill the feedback at the end of the session, and especially for Pak Doan student, we have a special link to for your attendance to this class to replace Pak Doan classes in Telkom University. So don't forget to capture this Zoom meeting as evidence that you are joining this class. So do you guys have any question? Hello, guys. Don't be shy.
Maybe have any voucher or discount product, maybe have any question?
Unfortunately, we don't have any kind of
any reward
that.
from the international office.
Yeah, I'm sorry, we don't have any kind of reward for this class. So maybe Pak Doan have a special reward for your student. So everyone, please don't be shy. If you have any question, just ask. Hello, students.
Yolanda mau nanya, Yolanda.
Yolanda, so please.
Belum ada, Pak.
Sudah mengerti Yolanda dari kedua speaker? Okay, we have a question from Harsat Mohammed. What are some everyday example where simulation and modeling are used? So maybe Pak Doan can answer first.
Maybe the question is general, yeah, I think, yeah.
Yes.
About the simulation and modeling. From the telecommunication engineering side is when we talk about the modeling and simulation use is for the uh, final project, yeah, final project, or in our the research, yeah, research purpose. Before we doing the research or final project, we should be define the objective or the goals of our research or final projects. Uh, and then when we have some the objective on the goal on the the purpose for our final project or research, we define or design the model system. Yeah, what the model system also the parameter or attribute in including in the model system. Sorry. After we define or design the model system and also the attribute on the parameter input the model system, we're going to the validate and verify the model system using the simulation tools. Yeah, this is the process when we work for the research or final assignment, final project in uh, in my class. I think it is for me, Pak Sina.
Okay, thank you for the answer. Dr. Helmi, would you like to add the answer?
Yes, sure. Thank you. So I would like to respond for the question. Actually, basically, whether we aware or not, we are using the simulation, modeling and simulation in every day, maybe every day. But in our life, for example, um, when we are using Google Maps or Waze in Malaysia, we are always using two types of what we call it as a traffic flow analysis software lah. Okay, so Google Maps and also Waze, for example, that we are using in Malaysia for planning our traveling, planning our route. It is also a real-time modeling simulations, whereby the system will our um, predict our range, okay, how many kilometers from point 1 to point 2, point A to point B, and also it's help in terms of not only for the range, okay, the kilometer, but also it's or include the simulation of time, estimate time arrival ETA. Okay, whether you are using car, motorcycle, and also if you are using, if you are walking, walking distance. So that is one of the sample of modeling simulation that we use every day. Including right now, if we activate our weather forecasting and in our smartwatch or maybe our Microsoft, your laptop or your tablet, and if you are activate that one, is also a simulation the weather forecasting and much more. So that is two example that I give it to answer the question. Thank you.
Okay, thank you for your explanation. Harsat Muhammad, do you get the answer? Okay, thank you. Is there any question? Anyone? there any more question?
Bandung is now heavy rainy. Malaysia is heavy rainy.
So,
Dr. Helmi.
right, during my presentation, and then the network is interrupt. That one, it is very rain heavily and also with thunderstorm. But right now it's okay. No raining, no thunderstorm. The weather also the cloud is very clear right now. So alhamdulillah. So after this, I will back my home with a very good weather.
Okay, I think if it's there is no more question, I think we will end this session. Is it okay? Pak Doan, Dr. Helmi, is it enough?
Enough.
Okay, so thank you everyone for coming to this session. So before we close this session, kindly open your camera. We are going to have a photo session first. So please, students and all participants, kindly open your camera. We are going to have take a picture. Please open the camera. Yolanda, Yusril, Malsa, Naufal, Dafa, Arya, Yasmin. Could you please open your camera? Okay, thank you. So I will count to 3. Okay. 1, 2, 3. Okay, one more. 1, 2, 3. So once again, thank you for everyone for coming to this session. Hopefully, this class will give you more knowledge about modeling and simulation on your daily basis. So thank you so much for coming here. Don't forget to fill out the feedback link and attendance list. So see you again next session. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Dr. Helmi.
Terima kasih Pak Doan, terima kasih Dr.
Terima
Helmi.
kasih Dr. Helmi.
Bu Indah. Ya. Thank you all.